Hey there, this is Hallie Abarca, and I'm going to introduce a new NASA Roses PDART task called MERIGOLD that my co-I Fred Califf and I recently had selected. So first, a little bit of background about the Mars Exploration Rover program. The two Mars Exploration Rovers, Spirit and Opportunity, were initially designed as 90-day missions, landing in Gusev and Meridiani. What started out as this 90-day mission turned into an overly successful 14.5-year MER program. Over the course of these two missions, they covered roughly 53 kilometers in combined routes and generated over 400,000 unique science data products by the onboard engineering and science instruments along the way. Within the large archive dataset, it's currently really difficult to understand the context of all of the science observation. There's currently no standardized map localization information attached to any of the MER mission science products. And while PDS datasets do contain the rover spatial position metadata, they're in different coordinate systems and not located relative to a unified base map. While some targets were able to be curated with links back to their observation in the publicly available MER Analyst Notebook, unfortunately the majority were not, and none provide a retrievable mapping coordinate. On the right here, we have an example of a curated target in the MER Analyst Notebook from Opportunity Rover with the location of an APXS measurement dotted in red and one of the MI microscopic images taken of that target. In response to these challenges came MERIGOLD, which stands for the Mars Exploration Rover In-Situ Global Observation Localization Dataset. So this is a newly funded NASA Roses PDART with work expected from 2021 to 2023. MERIGOLD will provide a unified map dataset of all of the MER instrument science observations for future research and education by the science community. The main deliverables of this task are localization datasets and overview maps. I will mention here that this task has heritage from MSL and was supported by the MSL project and the AMOS MMGIS task. The goals of MERIGOLD are to enable future researchers to 1. Be able to identify any observation that took place on a unified map Mars projection and coordinate system. 2. Determine what other instrument observations are coincident with that observation. 3. Determine whether observations overlap from multiple rover positions. 4. Provide spatial contacts between distant rover positions. And 5. Allow for critical ground-to-Earth observations from any Mars orbiter, whether past, present, or future. On the right here, we have an example from the Mars Science Laboratory Curiosity rover. The gray line is the rover path as the rover moved to different locations around here in this region, and the different colored circles are the mapped observations that were taken at the current and nearby rover positions along this zigzag route. Okay, so what is the dataset that we're talking about here as the deliverable? So the localized dataset contains a series of tables organized by rover and instrument. In each of these tables is a row for each instrument observation. And in each one of these rows is 37 metadata fields of metadata. The primary fields are localization information with additional metadata for identification, contextual information, and historical data of how it was localized. Digging into that a little bit more, the primary localization information means recording the observation's global northing, easting, and elevation, as well as the latitude and longitude. Then there are the PDS identifiers to find the original data product, mission and planning identifiers such as sequence and stall, instrument pointing directionality and range from this rover, the type of observation such as spectra, image, grind, maybe brush, the method that we use to localize the data product, the observation's coordinates and the different frames that were used to transform the position, and then the rover global localization, quaternion attitude at the time of the observation. And here we have one of two eye charts, just in case for any of those curious out there about what the full list of 37 fields are that we plan to include. You can pause here and read through, but we're just going to keep moving on. And our second eye chart that you may wish to pause, but again, we'll just continue for now. So getting into how this is actually achieved at a high level. So instrument localization processing is split up into 3 categories of instruments, mast, fixed, and arm, to get the observations into a consistent rover frame as our starting position for frame transformations. The first, mast-pointed instruments, are instruments that are able to be pointed to a location using the azimuth and elevation joints on the mast, which include the navigation cameras, the PanCam cameras, and mini-TESS. The second, we have our fixed and pointed instruments, which are rover body attached instruments, which include the front and rear hazard cameras. And lastly, the robotic arm, or instrument deployment device on MER, includes 4 instruments that are placed onto the Mars surface with the arm, which include the APXS, Moss Power, the rock abrasion tool Rat and Grind, and the microscopic imager. So as mentioned on the last slide, the data products are localized to the rover frame to provide an XYZ coordinate that is relative to the center of the rover. Much of the label metadata in the PDS labels is in this coordinate frame. On the right, you can see the example like red dot representing a data product in the rover's workspace. So from there, coordinates are transformed into local level frames, which is a frame that has been north aligned by using the rover quaternion. And again, on the right now, you can see that that north alignment has updated the data product localization and is actually in the southeast direction of the rover in its workspace. And lastly, the local level coordinates go through a linear transformation to a global frame using the global rover localization by the MER localization scientist for each unique rover position. And now here you can see we have the rover position in the global frame, where all observations from any rover position are now in their correct location. So getting back to how we got the observation in a rover frame, the first use case is fixed instruments. Now, these are the simplest of observations to localize. These are simply localized by applying a Cartesian offset to the rover frame coordinates. Second, we have the mast-pointed instruments that are located on the rover's PanCam mast assembly. These are localized by applying spherical to Cartesian coordinate transform and rate intersecting that with the surface to provide a central coordinate of the observation and rover frame. And for this task, we actually propose to project the localizations onto a flat plane at the rover's ground level. And the reason why we chose to do this is this keeps the resulting coordinates consistent in rover frame that can easily be updated if the rover localizations are remapped in the future. And lastly, the robotic arm instruments are localized using the data product label information, which includes the instrument position and pointing direction in rover frame. So using this with the length of the instrument or the recorded focus distance, which gives us the range to the surface, we can determine the location of the observation in the rover workspace. So for this task, we are using the publicly available base maps that are found in the analyst notebook and to calculate the rover elevations, which are not currently included in the delivered rover localization tables. We will be matching the high-rise orthomosaic and DEMS to the base map, and we will be including those type points in our final delivery. Okay, so how exactly does this all work? So one of the first MERIGOLD subtasks will be to write Python processing scripts to pull metadata from instrument PDS4 labels and generate the localization information. The Python scripts will rely on GDAL, which is an open source geospatial library, Vicar open source, and the PDS4 Python library. So for the MSL version of this task, we were lucky that the team was able to use a rover localization database, places to do the coordinate transforms between rover frame and Mars orbital frame. Instead, as part of this task, there are scripts to do the coordinate transform. We'll read in the MER rover localization files that we mentioned are in the analyst notebook, and all the information needed to update the localizations, if they are refined in the future, will be included in our archive. So for the base map generation and visual validation, we will be using Esri Arc Pro, and this will be an iterative process that will feed back into the localizations and likely into the scripts. And lastly, for the PDS4 label design, we'll be using Plaid provided by PDS Engineering Node, and once the archive bundle is generated, we'll be using PDS Validate for PDS4 product and bundle validation. So there are 2 parts to the final delivery. There is the primary delivery to the PDS IMG node, which are 2 PDS compliant formats and will have the appropriate PDS4 labels. So these are CSV and GeoCSV. So geospatial, comma-separated value files provide a similar format, but have the added benefit of including mapping, coordinates, and well-known text, which is an open source spatial format known in the mapping community. The secondary delivery will be to the PDS imaging annex, and these are going to be two commonly used mapping product formats that are not PDS compliant currently. And these are GeoJSON, which is just an ASCII web-enabled format, shapefile, which is used by all major commercial and open source mapping programs, and last but not least, there will be an set of overview maps that will be delivered as GeoTIFF to the annex, meant as a visual quick look of the data products. And an example of these overview maps is on the right from MSL. This shows around 3,000 DAN observations at over 800 rover locations over the course of 2,000 sols. So the PDS peer review for this will be taking place in spring of 2023. Please feel free to reach out to me if you have any questions, feedback, or are interested in participating as a peer reviewer. And thank you for watching.